All right, so again, today what we're gonna do is look at graphs for sine and cosine functions and use the unit circle to do so. So the sine and cosine functions are different than a lot of the other functions that we've talked about because the sine and cosine functions are what we call periodic. So a periodic function is a function for which the outputs repeat at regular intervals. A mathematical definition is that when a function is periodic, then that means that f of x equals f of x plus p, meaning that the output at 1x is going to be the same as the outputs p units later for some real number p. This means that every p units, the function's outputs repeat themselves, and the smallest such value of p is called the period. So what we're going to do is make a table of values to determine what the graph of y equals the sine of theta would look like. Now, normally what we do is we substitute things like -2, -1, 0, 1, and 2. But because theta is an angle measurement, let's put in special values for theta that we learned from the unit circle. So let's think about our unit circle, okay? And let's go around the unit circle and think about all the sine values. On the unit circle is sine x or y?
Y.
Good, okay? So let's think about the y values as we work our way around the unit circle. So when theta is 0, what's the y value? 0, okay? What about when we move up to pi 6? What's the y value? A half. What about pi 4ths?
That's
Root 2 over 2. Pi 3rds? Root 3 over 2. And pi halves? 1, okay? Now let's keep going. If we keep going to 2 pi 3rds, the root 3 over 2, good. 3 pi 4ths, root 2 over 2, 5 pi 6, 1 over 2, and what about when it's at pi? 0, okay? Now what happens when we start 7 pi 6? -1/2. And then negative root 2 over 2. And then negative root 3 over 2. And then when it's down here, -1. And let's work our way back up. 5 pi over 3 is negative root 3 over 2. 7 pi 4ths is negative root 2 over 2. 11 pi 6 is -1/2. And when we get back to 2 pi, the value of y is 0. So then what about at 13 pi 6ths? Back to 1/2. What about 9 pi 4ths? Root 2 over 2. 7 pi 3rds. Root 3 over 2. 5 pi halves. 1, okay? Do you guys notice, and I know that we had a lot of the same values, but do you see that once we get to 2 pi, the values start repeating themselves exactly again? So note that the y values begin to repeat themselves when theta equals 2 pi. And what that means is that the period of the function, f of theta equals sine theta, is 2 pi. And what we'll see when we graph is we're going to see things repeat themselves every 2 pi. And we'll see what that looks like in a little bit. Okay? We're going to plot these using the decimal approximations. But before we do that, let's label our axis here. And what I'm going to do is label the big quadrantal angles. So like on this heavy tick mark, I'm going to label that pi halves. I want you guys to do the same. Okay. This is going to be then pi. So every tick mark at this point will be pi halves. So the next one will be 3 pi over 2. The next one will be 2 pi. Next we'll have 5 pi over 2 and 3 pi. 7 pi over 2 and 4 pi. And I'll have this 9 pi over 2 here as well. Okay. I also would like us to label the other side, negative pi over 2, negative pi, and negative 3 pi over 2. Okay. And what we'll do is we'll plot these points. So before we label our y-axis, let's, will we see that we're going to be going from 0 to 1, down to 0, down to -1, down to 0, or sorry, up to 0, up to 1. So let's not make this 1, just to kind of see what the shape is. Maybe let's make the 1 up here so that that way each of these is like 0.2. And then likewise, we'll go by -0.2s on this part of the y-axis as well. And so we've got our axis set up. So let's now look at what these decimal approximations are going to be that we're going to plot. Obviously, the ones with 0 are easy. Those are always just 0, right? Okay. 1/2 we know is what is a decimal? 0.5. So we can put 1/2 is 0.5. This 1/2 is 0.5. This -1/2 would be -0.5. Here's a -0.5. Here's a 0.5. So we'll just fill all those in. Okay. What happens when you find the square root of 2 over 2? What does that end up being? Just to one decimal place. What do you get? You take root 2 over 2. You can use your calculators if you want, obviously. What do we get when we take root 2 over 2? 0.7-ish, okay? So this is about 0.7. So that means that this root 2 over 2 is going to be about 0.7. This will be -0.7. This will be -0.7. This will be about 0.7. Okay. And what about root 3 over 2? 0.86-ish. Do you guys want to call that 0.86 or 0.9? What do you want to do? 0.9-ish? Okay. Okay. And then we just have the ones left, which we know is going to be 1, -1, and 1. Okay. So now let's try to plot these points on our graph. Okay. So we're going to start at 0, 0. The next thing we need to plot is pi 6, 0.5. I want you to think about what pi 6 is in relation to pi over 2. Remember that pi 6 is about 1/3 of that. So between here and here, I need you to at least mentally think about dividing that into 3 pieces. Do you guys see if I kind of like and I don't need you to put tick marks the whole time, but do you understand what I'm saying about dividing this into 3 different pieces? So what that means is that this is pi 6, this is 2 pi 6, which is like pi thirds, and then this is like pi halves. That makes sense? Okay. So we said the first one was going to be, this first little tick mark here is pi 6. And we said that pi 6 has to go to 0.5. So that's going to be about right here, between 0.4 and 0.6. Now, the nice thing about pi fourths is that that's this line that's drawn for you. That's right between the 0 and pi halves. So at pi fourths, that's going to be at about 0.7. Now, here we said that this was 2 pi 6, which is pi thirds. That's going to be, we said at about 0.86 or about 0.9, so maybe about here. And then pi halves is going to be 1. Okay. If you need to, again, kind of like divide it into those pieces for the moment, we won't always have to do this. We're just trying to get a sense of the parent graph. So this would be 2 pi thirds, which would be at that 0.86. This line would be 3 pi fourths, which is going to be 0.7. 5 pi 6 would be 0.5. And then pi is at 0. Okay. What shape does that kind of look like so far?
A rainbow.
It does kind of look like a rainbow. It's like a parabola-ish, right? Okay. Well, let's keep going and see what happens. So next we have 2 pi thirds. So are you guys seeing that like the that they're going to be kind of like close to the middle, like closer than that? So I'm going to go kind of close to the next line that is drawn. And I need to, and that's going to be my 7 pi 6. That's going to be -1/2. So the line is actually 5 pi fourths. That's going to be -0.7. A little bit to the right of that is 4 pi thirds. That's going to be the -0.86, so about 0.9-ish. And then 3 pi halves is at -1. Does it look like a parabola anymore, or does it look like it's a little bit different over here? It's a little different, isn't it? So let's see what happens next. So we go to the right, 5 pi thirds is going to be -0.9. This line, 7 pi fourths, is going to be -0.7. A little bit to the right, that 11 pi 6 is going to be -1/2 or 0.5. And 2 pi, we're back to 0. And if we plot the next ones, 13 pi 6 is about 0.5. 9 pi fourths is going to be at 0.7. 7 pi thirds is 0.86. And 5 pi halves is at 1. Do you guys see that this looks like it's going to be repeating in this fashion? And what I'd like us to do is, just for now, I want us to kind of trace at least this first period from 0 to 2 pi. It's curved, okay? So it's not pointy. It's a beautiful, beautiful curve, okay? And that is what the sine function, one period of the sine function, looks like. Weren't the easiest points to plot at 0 and 1 and -1? Why don't we follow that pattern throughout? What do you think would happen at 3 pi? Where would that be? Back to 0. What about at 7 pi over 2? Is it going to go up to 1? -1, good. And what about 4 pi? 0. What about 9 pi over 2? Up to 1, good, okay? And without all those points, do you guys see that that pattern would just continue in that fashion? Let's work backwards too. What do you think would happen at negative pi over 2? -1, very good. And then at negative pi, 0. And at 3 pi over 2, 1, good. Okay. And that, my friends, is what our sine function looks like. Do you see that if you think about it, like we start here and then it starts repeating again here, okay? What that means is that this is one period of the function. And that's 2 pi units for that parent function for sine. Okay? In our next lesson, what we'll do is we'll look at how we could affect the period a little bit and some other pieces as well. Okay? Are we okay with that? So that's our sine function. What I'd like us to do now is I'd like you guys to do the same thing for y equals cosine theta. Now, when you think about cosine on the unit circle, is cosine x or y? X. So now I'd like you to think about the x values as you go around the unit circle, okay? So I'll give you guys a couple minutes to fill that in. Okay, so these are the values. This time, when we start at 0 and we think about the x values, the x value at 0 is 1. Then root 3 over 2, root 2 over 2, 1/2, 0. Then we start getting into negative x values, etc. Do these look okay? All right. So once again, when do the y values start repeating themselves in the table? Yep, when theta equals 2 pi. So again, what that means is that the period of this function, f of theta equals cosine theta, is also 2 pi. And that just means it's going to repeat itself every 2 pi. Okay? Once again, let's see what the graph looks like by labeling our graph. And we're going to label it at pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, etc. Okay. And also please label some of the negative values as well. So basically we're labeling on those large tick marks that I have there for you, the quadrantal angles. Okay. And I think our scale on the y worked out for us very well last time as well. So I'm going to once again just go by 0.2s. Again, we won't do this forever, but we'll just do this for today. And then we can start plotting, okay? This time, our first point is going to be at 0, 1. Again, when we think about it, our pi 6 and pi thirds are going to be if we divided these two boxes into 3. So at pi 6, that's going to be the 0.86 or about 0.9. The pi fourths is that 0.7. The pi thirds is the 0.5. The pi halves is the 0. Okay, again, if you need to think about dividing it into thirds here, the 2 pi thirds is negative 0.5. 3 pi fourths is negative 0.7. 5 pi 6 is negative 0.86, about negative 0.9. Pi is negative 1. And as much as that might seem like it's a straight line, do you guys see it is not a straight line? That it's having some curvature to it. And filling in the rest might help us get the type of curvature we're looking for. So then 7 pi 6 was negative 0.9. 5 pi fourths, negative 0.7. 4 pi thirds, negative 0.5. 3 pi halves, 0. Okay, again, 5 pi thirds, 0.5. 7 pi fourths, 0.7. 11 pi 6, 0.86, about 0.9. 2 pi is up here at 1. Then we have 13 pi 6, about 0.9. 9 pi fourths, about 0.7. 7 pi thirds, about 0.5. And 5 pi over 2, 0. Okay? Did we just graph one period only? No. Where does it seem to start repeating? Again, at 2 pi. And so if we connect these, okay, once again, this is what one period of our cosine function looks like. It's not really a ton like a parabola because you see how it kind of curves at the ends there, okay? So we have to make sure that when we have those cosine that we have it kind of looking like that, kind of like this little valley that's here. And we can see that we continue down this way as well. Let's keep going and let's extend that pattern. So 5 pi halves ended up being 0. What would 3 pi end up being? Negative 1. How about 7 pi halves? 0. How about 4 pi? 1. How about 9 pi halves? 0. Awesome. And we can connect it like this. Okay. What about going backwards? What does negative pi over 2 look like? Where do you think that would end up? Back at 0. How about negative pi? Negative 1 and negative 3 pi over 2, back at 0. Okay. So these look very similar to each other, don't they? Except they have different starting points. Where did sine start? Sine started at 0, but cosine started at 1, okay? So what we've really done is we've taken the unit circle and we have made it into this graph. And so this is just a little animation here. And as it goes around, I'm going to wait till it completes the circle. I'm going to start the animation and it's going to start graphing the sine function as it moves around the circle. Okay. So isn't that what we really did with our table of values? Okay. So that's what happens when we have the sine function. Okay. Now let's look at the cosine function. Isn't this what happened when we graphed our table of values? And do you see that we keep going around the circle? And so you can keep going around the circle, and that pattern's going to keep repeating itself over and over and over again. And that's the idea of those periodic functions, okay? So now that we've done that, I want to introduce a couple more definitions to you, okay? If we have something called, there's something called the midline. And some teachers might call it the axis of a trig graph for sine and cosine. This midline is the horizontal line halfway between the maximum and minimum points of the graph. Okay, we'll look at that in a second. And another word I want us to know is I also want us to know the word amplitude. The amplitude of the function's graph is half the distance of the maximum, big M, and the minimum, little m, or half m minus big M minus little m. You can also consider it the distance from the midline to any maximum or minimum. And we'll talk about what the amplitude of these graphs is in just a second. Okay. Now, let's think about the domain of each of these functions. The domain of each of these functions is going to be what we looked at. Did we have any place where it stopped, or did it keep going left and right forever? Left and right forever. What does that mean about our domain? That it's all real numbers, okay? Or in interval notation, negative infinity to infinity. And that was true of both the functions, right? Both sine and cosine functions. Now, was the range of these functions all real numbers as well? No. What was the range of each of these functions? Was there a low point and a high point for each one? -1 was the low point and the high point was +1. So in inequality notation, we can say that y is greater than or equal to -1 and less than or equal to 1. Or in interval notation, we can write it this way. Well, we just defined the midline. It's the horizontal line halfway between the maximum and minimum points. If I look at the sine function, what's halfway between 1 and -1? 0. So isn't it y equals 0? That would be our midline. What about for the cosine function? It's also at y equals 0. So the midline of each function is y equals 0. And for these parent functions, do you guys notice that that's the same as the x-axis? Now let's look at the amplitude of each function. The amplitude of each function is half the distance from the of the maximum to the minimum, or the midline to the maximum or minimum. What's the distance from -1 to 1? That's a distance of 2. And what's half of 2? 1. Also, how far is it from our midline to 1? Or for the midline to -1? Also 1 unit, right? And isn't that the same thing for the cosine function as well? So what that means is that the amplitude of these functions is 1. Next, let's look at the x-intercepts of sine of x. Let's look at my graph. I don't need you to look at yours. We'll look at mine. And let's just work from left to right. Where's the first x-intercept that you see? -pi. Where's the next one? 0. Where's the next one? The next one. Next. Next. Where would the next one be? 5 pi. Good. All right. So let's just list that here. Okay. So they're at negative pi 0, 0, 0, pi 0, 2 pi 0, 3 pi 0, 4 pi 0. And I know that that's all that's in our graph, but it was pretty nice to establish that pattern. God bless you. Okay. Now, are the x-intercepts at y equals cosine theta the same? Let's look. Where's the first x-intercept that we saw in our graph here? Negative 3 pi over 2. By the way, is that the farthest left x-intercept that exists, or are there other ones? There are other ones, but we'll start there. So we have negative 3 pi over 2, and then negative pi over 2, and then pi over 2, and then 3 pi over 2, and then 5 pi over 2, 7 pi over 2, 9 pi over 2. What would the next one be? 11 pi over 2. So kind of like the odd numbers over 2 there. Good. So let's start writing those. So negative 3 pi over 2, 0, negative pi over 2, 0, pi over 2, 0, and then we basically have all of the pi over 2 values that are not pi. So we saw one at 9 pi over 2, but we know that if we continue that pattern, it would be at 11 pi over 2, 0, and keep going in both directions, positive and negative. Okay. So now let's look at the maximums of sine of x and where they occur. Okay. So this first maximum is at negative 3 pi over 2, 1. The next one is not at negative pi over 2. Where's the next maximum? It's at positive pi over 2, comma 1. The next maximum is at 5 pi over 2, 1. So this isn't every pi. Do you see that the maximum is every 2 pi? And so then the next maximum would be at 9 pi over 2, comma 1, which we do see in our picture. So now let's look at the minimums of y equals sine of x. My minimum was at negative pi over 2, negative 1. The next one was at 3 pi over 2, negative 1. The next one is at 7 pi over 2, negative 1. So again, how often are my minimums occurring? Every how many units? Basically every 4 pi over 2, right? Okay, which is every 2 pi. So if my last, oh, these should be negatives, sorry, negative 1. Okay. So if the last negative that we graphed was at 7 pi over 2, negative 1, where would the next minimum be? If I add another 2 pi to that, that would be 11 pi over 2, negative 1. Okay. Now that we've done that for sine, why don't you guys look at my graph so you don't have to flip back and forth, and take a minute and write the values for the maximum points and minimum points for the cosine function? Take a minute and do that. And fill in all the blanks, even if they're not on the graph. Okay. We about set there. Hopefully for our maximums, you saw that would be at 0, 1, 2 pi 1, 4 pi 1, 6 pi 1. So again, every 2 pi. And then the minimums were at negative pi negative 1, pi negative 1, 3 pi negative 1, and you'd find another one at 5 pi negative 1. Okay. And then again, it just keeps going in each of those directions. So that's a little bit about these parent functions. What we're going to do to these parent functions, like we usually do, is we're going to introduce our old friends. Do you remember our transformation friends? What were their names? What letters were they? Oh my goodness, we're going to need to meet them again. A, H, and K. We're going to meet our friends A, H, and K, and we're going to have a new friend, B. And what B is going to do is B is going to affect the period of the function. So before we do that, though, let's just make sure that we're okay with the idea of the period and amplitude and what these shapes are. If I'm looking at example 2A, let's look at the period. To find the period, you want to look at where it starts and then where it stops. So a lot of times, like this looks like we could see a starting pattern at the axis. And I have some students tell me that the period is 6 pi because that's where the end of the graph is. But is that where the pattern starts repeating itself? Where does the pattern start repeating itself again? At 2 pi? At 4 pi. Do you guys see that that is an example of the period? So our period here goes from 0 to 4 pi, which means our period is 4 pi. Okay. If we look at our amplitude, the amplitude, again, is half the distance from the minimum to the maximum, or you could take the distance from the midline to a minimum or midline to a maximum. What does the amplitude of this graph appear to be? So how high does the graph go up if we look at our axis? Okay, so when we look, it goes from -3 to 3. So thinking about the actual definition, how far is it from -3 to 3? 6, and what's half of that? 3. So that's our amplitude. And is the shape of this, like the shape that you see, is that closest to y equals sine of x or y equals cosine of x? Based on where it starts. This one started up at 1, right? Which is closest to y equals cosine of x. Let's do the same thing in letter B. Let's look at our period. It looks like I could start here. Where does it appear to end? So if I'm starting here, then it could end here. Do you guys agree with that? And so that's going from 0 to 4. So our period is 4. What about our amplitude? How far is it from -2 to 2? 4 units, and what's half of that? 2. And if we think about our midline at the axis, notice the high point is 2 away and the low point is 2 away. And if I'm focusing on this shape, what shape is that closest to? Y equals sine of x. Now, the interesting thing about trig functions is that isn't it possible that someone else could have went from here to here? Okay, with that, I did it in really light yellow. Still, the period would be 4 and the amplitude would be 2, but that's closest to y equals cosine of x because they're really just shifts of each other, okay?